Now when we are discussing the various state space representations of discrete time systems, we have discussed already controllable canonical form, and now we will be discussing observable canonical form, which is obtained by this method, which is called as the nested programming method. Now consider any pulse transfer function system matrix y of z by u of z is equal to b0 plus b1 z inverse plus b2 z power minus 2. Any matrix can be, any system transfer function can be written in this way: z power minus n 1 plus a1 z power minus 1 a2 z power minus 2 plus an z power minus n. Now when we are having this and we are required to convert this matrix or pulse transfer function matrix into the observable canonical form. This matrix is converted into observable canonical form using nested programming method. For this, let us say we are cross multiplying everything on both sides. If you cross multiply on both sides, we will be having y of z plus a1 z inverse y of z plus a2 z power minus 2 y of z plus so on an z power minus n y of z, which is equal to b0 u of z plus b1 z inverse u of z plus b2 z inverse z power minus 2 u of z plus so on plus bn z power minus n u of z. Now bring everything to the left hand side. When we are having this, you can say that we have y of z and you are having all these minus b0 u of z, y of z minus b0 u of z is brought here, then plus a1 z inverse y of z minus b1 z inverse u of z. I am trying to arrange all the similar powers of z at one place so that I can manipulate it to a great extent. Minus b2 z power minus 2 u of z. Right, so we have finished this, plus so on plus an z power minus n y of z minus bn z power minus n u of z. Now this entire equation is brought down to this shape. Right, so when we are having this y of z, if you can take it to the y of z is kept at the left hand side, and if you are taking this all these equations to the right hand side of this, you can say that we are having b0 u of z plus z inverse plus, if you consider only these two, then you are taking it to the right hand side, you can say that we are having positive b1 uz minus a1 y of z plus, when you are considering these two, you can say you are having z power minus 2. You have z power minus 2 here, b2 u of z minus a2 y of z plus so on plus, you can go here and we have z power minus n, z power minus n into bn u of z minus an y of z. Now this is your final equation or manipulated equation from this equation. when you are having this, now you can say that we are going for nested programming method. Now if we can nest all these z inverses, you can go in this form. You can simply write this equation this simple equation as y of z is equal to b naught u of z plus, you can take z inverse common everywhere, so you can say that it is z inverse into, open a parenthesis, b1 u of z minus a1 y of z plus, again plus z inverse of a square bracket z inverse of, because I have z inverse into z inverse, I have multiplied these two, I have z power minus 2, therefore b2 u of z minus a2 y of z plus, again some z inverse into, you can say b3 u of z minus a3 y of z, again plus, you can go down and you can say the last equation z inverse of, when you are having all this, I will again write, use another brace like bn u of z minus an y of z, So I close this bracket here, the other brackets are closed here, and this one and this one. For example, let us say we are having such type of equation, when this equation can be written in this form, that is, you have z power minus 1 into minus 1 minus 2 minus 3 so on n times this z power minus n. So you get z power minus n here. So everywhere this equation can be written in this form. So now to define our state variables, from this single equation that we are dealing with, I can write this y of z is equal to b naught u of z plus xn of z. Let me consider this entire equation as xn of z. Right. So when I consider xn of z is equal to z power minus 1 into b1 uz minus a1 yz plus, I will write this as xn minus 1z, that is z inverse into b1 uz minus a1 yz plus this entire thing I can write it as xn minus 1 z. Okay. Now what is xn minus 1 z? That is again z inverse b2 uz minus a2 yz plus xn minus 2 z. Right. So this goes on like this, and you can write, if I put n is equal to 2, x2 of z is equal to z power minus 1 into b n minus 1 uz minus a n minus 1 yz plus, when you are having n minus 1, it is n minus 2, therefore x1z. And what is x1z for us now? That is Z inverse into Bn Uz minus An Yz plus this is not existing, therefore you have this. So from this equation we have obtained these equations. Now once we can finish this here, once we are having this here, now all these equations, when we are applying inverse Z transforms to these equations, we can say that y of k is equal to, from this equation you can say it is b naught u of k plus xn k. Now the remaining all these equations, Z inverse, if I take it to the other side, it is Zxn z. All G inverses I can consider it in this form, Z x2 z, and if I remove this I have a Z x1 z. Now if I apply inverse Z transform to this Z xn z, it is nothing but xn k plus 1. Or I come in the reverse way, Z x1 z, you can call it as x1 k plus 1 is equal to, this equation is equal to minus an yk plus bn uk, right. And when you are considering it here, Z x2 z, now this equation x2 k plus 1 is equal to minus an yk minus an minus 1 yk, or instead of that, first I will write this plus x1 k minus an minus 1 yk minus an minus 1 yk plus bn minus 1 uk plus bn minus 1 uk. Similarly, when you are going down here, z into xn minus 1 z, so xn minus 1 k plus 1 is equal to xn minus 2k minus a2 yk minus a2 yk plus b2 uk, and similarly z into xn z can give us xn k plus 1 is equal to xn minus 1 k minus a1 yk plus b1 uk. Now we have all these equations used here in the discrete time instance, and we have all these equations x1 k plus 1, and when we substitute y of k here, this equation y of k, or equation 1 for example, let us say, is substituted here and here, then we get the final state equation that we are deriving for. So from this we can say that we are having x1 k plus 1 is equal to minus an into yk is b naught uk plus xn k plus bn uk, or you can write this as minus an xn k plus bn minus an b naught uk, that is x1 k plus 1. So this is our second equation. Now what is our third equation that we are going to get from here, x2k plus 1. x2k plus 1 can be written as, or this is important for us, we will use it in the later part of our derivation. x2k plus 1 is equal to x1k minus an minus 1 into y of k is again b naught uk plus xnk plus bn minus 1 uk. Right, so you can write this as x1k minus an minus 1 xnk plus bn minus 1 minus an minus 1 b naught into u of k. This is x2k plus 1, and this is our third equation. This is the third equation. Now we will go for this. Xn minus 1 k plus 1 can be written as xn minus 2k minus a2 into b naught uk plus xnk plus b2 uk. Now if you can rewrite this equation, you can write it as x minus 2k minus a2 xnk plus b2 minus a2 b naught uk. Now this is equation 4. For example, let us say this, and when we are going with this, you can directly write it as xn k plus 1 is equal to xn minus 1 k minus a1, y of k is b naught uk plus xnk plus b1 uk. Now when you replace this here, you have xn minus 1 k minus a1 xnk plus b1 minus a1 b naught uk. Now equation 5. Now putting all this 1, 2, 3, 4 and 5 equations in a single go, you will have all this. You will have the observable canonical form. So what are the equations that are required for us? You have these equations, you have this, and you have this equation k plus 1. So this equation and xn k plus 1, and we have got this 5 equations, and all these 5 equations can be put in one place. You can say this as x1 k plus 1 is x1 k plus 1, x2 k plus 1. You can have a small division here, so on, xn minus 1 k plus 1 and xn k plus 1. When we have written this, you can write it as, you don't have x1k, x2k, so on up to xn minus 1k. So you have bn minus an b naught uk. So you can write 0, 0, 0 and minus an into x1k, x2k, xn minus 1k and xnk plus uk. You have this plus bn minus an b naught into uk. bn minus an b naught into uk. That is a single equation. Now x2k plus 1, it is 0, that is 1, x1k 1 1 into x1k minus an minus 1 xnk. So 0, so on, 0 minus an minus 1 xnk plus bn minus 1 minus an minus 1 b naught uk. So this is done. Now the third equation, this is going on to the last second penultimate equation that we are going to write, and here it is xn minus 2k, or you can say that 0 0, and this is also 0. You can say you have 1 here, and minus a2 xn minus 2 plus b2 minus a2 b naught uk, and this equation can be written as, this is the last equation, therefore 0 0 0 1 minus a1, xn minus 1 and is 1, and the coefficient of xnk is minus a1, and therefore you have here b1 minus a1 b naught. So this is the state equation of the observable canonical form, and eventually with this you can simply write y of k in the equation form. You can write that in the equation form, y of k is equal to 0 0 0 1 into x1k x2k xn minus 1k and xnk plus b naught u of k. So these are the state equations of the state space representation of the observable canonical form of a discrete time system, which is using the nested programming method. We call this nested programming method because we are using in between z inverses in many stages, and we are trying to utilize it to get this equation. So eventually when you are going for y of z by u of z, you have obtained this method from b naught plus b1 z inverse b2 z power minus 2 plus bn z power minus n by 1 plus a1 z inverse a2 z power minus 2 plus an z power minus n. Now when we are having these equations, you can just simply state that we are having the identity matrix in this area, and the first row you have, and the last column you have minus an minus 1, so on up to minus a1. Alright, and this, now when you are comparing the controllable canonical form and the observable canonical form, you can say that, if you can say that x of k plus 1 is equal to g x of k plus h u of k, and y of k is equal to c x of k plus d u of k. Now if this is for controllable canonical form, then for observable canonical form you can say that you are having x of k plus 1 is equal to g transpose of x of k, z transpose into x of k, plus here you have c transpose u of k. This is the transpose of the H matrix in that equation, and y of k is equal to H transpose of x of k plus du of k. So these two are completely related, and they can be obtained by the given pulse transfer function matrix, which is given to you in this form, and all the coefficients are given. The denominator coefficients are written in this form, minus an minus 1 minus a2 minus a1 so on, right? And you will be obtaining the observable canonical form in this process.